let you know why I've been somewhat absent on my channel over the past few days. This channel so far has been my feeble attempt to get advanced science out to all of you. Topics have ranged from the intricate ties between electromagnetism and topology using Chern-Simons theory, learning about some biophysics from the perspective of Brugada syndrome, the unique relationship between modern physics and economic systems, the strange curvature of space-time through Einstein's theory of general relativity, ways that we can quantize the forces of gravity, and the counterintuitive nature of quantum fields, along with many other topics. All of these topics are not for the lighthearted individual, but rather for those who want to genuinely understand the world around them and don't spew cliches like this, for example.
My goal is to have the best understanding of reality that I can, and for other people to do so as well.
Furthermore, given the current political climate, universities are in dire straits right now. Podcasters and political commentators try to make a name for themselves by trying to brush off the intellectual rigor of people who get PhDs and master's degrees. People like Dave Farina, Stephen Bennell, Matt Walsh, Andrew Wilson, and many others are just a few examples in a pool of many who are either failed academics or have no formal educational background. Yet, they pass as people who are taken seriously in the eyes of the public. This is a big problem. As we have seen recently, the political commentator Dave Smith on the Joe Rogan podcast claimed that you don't need a PhD to have an opinion on history.
To me, but I don't quite get what's all the appeal to authority stuff. I mean, you have to be an expert, or
no, I think
what
authority
exactly
matters. I think authority matters.
Or the billionaire Chamath claiming that going to university is stupid.
People, it's like a bunch of us were tricked to go to university, get $200K in debt to take a degree in art history, which was stupid. Mm-hmm. Instead you should have just gone to a trade school and made $150K a year and had a good life.
While there may be some truth to what they are saying, we should not listen to them, or at the very least, regard what they are saying with a grain of salt. It is for this reason I have decided to launch a new set of projects. I have decided that I want to expand the channel by attempting the impossible, animating all of these topics plus more. Over the past few days, I have been practicing and coding up animations to illustrate these concepts in more intuitive ways. Animating, for example, how ion channels act in the presence of different types of drugs, or making cool animations to try to illustrate Hawking radiation in the context of general relativity. All of this is part of a bigger ambition of mine, which is to develop an online program where you will be able to access a wide library of advanced topics taught in nuanced ways. Don't worry, I will still intend to keep on producing my original style of content, as this is the quickest way for me to create that content. If you wish to contribute to the channel, make sure to hit that like and subscribe button, visit my Patreon page, or become a member on YouTube. Now let's continue with the channel content. Okay, so the Kerr black hole, what we're going to do now is we're going to talk about, so we talked about the Schwarzschild metric, now we're talking about the Kerr metric. In the Schwarzschild metric, the case was we had a black hole and nothing was going on with the black hole. So if we draw this out, if we try to conceptually understand what the Schwarzschild metric was, it was a metric that said, you have some, like a black hole here. If we have a black hole, right, I'm going to move my iPad a little bit. Here's our black hole, and we are standing somewhere near the black hole. Well, the black hole is warping space-time, and we're standing, I'll reduce the thickness of my pen here. If we're standing, say, right here with a ruler and a clock, the metric G mu nu is going to tell us everything we need to know about how the clock is ticking and what the ruler is telling us, what an inch looks like when we get closer or further away from the black hole. So this here is our black hole, or this is our black hole. And in the Schwarzschild case, this black hole was not doing anything. It was just a static black hole, and it was really anything that we needed to know about the nature of our clock and our ruler just depended on how far we were from the center of the black hole. Okay. All right. In the Kerr case, the black hole is going to be spinning, and there's going to be a few things that we want to take a note of when we are taking a look at the Kerr metric. So the Kerr metric, again, suppose we have a black hole, and the black hole is, I'll thick my pen up again here. Here's our black hole. No, not red. We want a black hole here, but in the Kerr case, it's spinning, okay, and we want to assume, we're going to say, well, okay, it's spinning in the azimuthal direction here. We're standing somewhere near the black hole. We want to know what our metric is at this point, okay, and we're going to also assume that as it's spinning, it elongates in the direction it's spinning a little bit, right? So we're going to use a slightly different coordinates. We're going to use a slightly different geometry to understand this. And we're going to say, what we're going to do is we're going to say, okay, so if the degree to which it's spinning is telling us the degree to which it's elongating a little bit. You can imagine like spinning silly putty around or something like that. If you spin it around a lot, it's going to have a shape maybe that looks like this. If it's not spinning around a lot, it'll be more spherical. So in the case where the thing that's going to tell us, again, the radius of the black hole is going to tell us, so it's something we're going to need to know. But then this radius here is also going to tell us something. This is going to be A, this is going to be R, and so when R gets small, A is going to get large, okay, and there's going to be a point at which it becomes spherical, okay. And the point at which it becomes spherical is the point at which it stops rotating. So we want to say, so what I'm saying sort of in long way is that in the limit that R and A here and the speed of the rotation, in the limit that all goes to 0, we recover the Schwarzschild metric, because the Schwarzschild metric ultimately was a solution to our Einstein field equations. And so now what we're going to do is we're going to say, we're going to apply some spin to this black hole, not like particle spin or anything like that. That we'll get into later. We're going to apply some spin to this black hole, but in the limit that it's slowing down, then we recover the Schwarzschild metric. So let's go ahead and start investigating what this metric looks like. So we're going to have, and forewarning, there's going to be a lot of math in here, right? If you're not someone who likes math, you could skip to the end. If you are someone who wants to look more into the rigorous detail of the math, then continue watching. Okay, so here we have our metric, right? So in this case, we're going to add a condition that says our black hole will be axially symmetric. Okay, that just means it's a sphere it's a sphere or an oblate sphere. It's going to be axially symmetric. It's symmetric down this axis. Okay, this means that the metric for the black hole will be symmetric everywhere except for the time component and the azimuthal component, because it's not going to be, because it's spinning here, right? So this thing here is going to couple time with the spin, right? Because 0 is associated with the time, 3 is associated with the azimuthal component. That means this is going to be non-zero. All of these guys are going to be non-zero, right? Because these guys are non-zero in the Schwarzschild metric, and then everything else is going to be 0. So right off the bat, we can cancel a lot of these metrics out because we're assuming some things. Okay. So now what we're going to do is we're going to say, okay, so here it is, right? So G00, this is for our time, the time component of our metric. G03, G03 is going to be this guy, and that's going to be the coupling of the time with the azimuthal component. And then we have G33, that's going to be this guy right here, and then this guy right here says G11, G22, and then G21 and G22, that's going to be a coupling between dr, so the radius, and the angle, right? So like this, and these guys are going to be coupled, right? Because this guy's going to squeeze down, and so the angle by which you're turning around you're going this way, right? So there's two different angles, right? There's this angle, and then there's this angle, and we're saying that this angle is related to the value a here. Even though we don't have a here yet, that's really what this is saying. This is saying that we have a coupling between r and theta. This is just a picture, right? So you go forward in time or back in time here. This is right. So this is our theta. These are the angles phi, our azimuthal angles, and then the radius as well. And we can say we have a metric anywhere along this black hole, and that's going to be dependent on all of this dr, d theta, d phi, and so forth. Okay. All right. So we rewrite our metric in this way. Okay, so ds is going to be this guy here. Again, that's just this guy right here. 0, 3, that's going to be the coupling of time and the azimuthal angle. 3, 3 is going to be for the azimuthal angle itself. And then g alpha beta, this here is going to be, this is clearly a two-dimensional metric, right? So that's this little, it's sort of not a two-dimensional metric, it's a matrix, right? This is a matrix that's sort of embedded in a larger matrix, okay? And so any two-dimensional metric can be conformally transformed into a flat metric, which means that our off-diagonal components can go to 0, so our line element now becomes this right here. So this guy is TT, this guy is TR, right? Oh no, that's TR, right? Not T theta. T theta is this guy, which is this guy. TR, theta, theta, and then our azimuthal angle, right? So at this point, we're saying that this guy here, we're going to assume here that this guy right here is, we're not going to have coupling going on now. Well, it might make sense that these things might be coupled, but what we're going to assume here for the Kerr metric is that they actually are not. All right. Okay, so furthermore, if for any reason the black hole stopped rotating, we'll say that the metric reduces down to the Schwarzschild metric. However, in a slowly rotating black hole, in the weak approximation, we will add a correction term to the line element. So in a non-relativistic case where the mass is very small or the radius is very large, then this is going to reduce down to the Schwarzschild metric. So we're adding this correction term. This correction term, it's a coupling again between the azimuthal angle and t. So this black hole is rotating. Okay. I don't want to get far away from the mic. The black hole is rotating. So as it's rotating, it's lengthening out. Okay. It's rotating in time. So the two things are coupled. And this we can sort of intuitively think, well, this is going to be related to the angular momentum of the black hole, right? Because it's spinning, it's got some momentum, it's got some mass. And so we're going to say that J here is going to be thought of as sort of the angular momentum term, right? So where J is, it's related to angular momentum times the frequency by which it's rotating. And I, as we know, is mr squared. That's the inertia, right? And then so that's going to be related in this way, okay? Because omega is r over v, or yeah. So v over r. Sorry, right? So the velocity of the rotation divided by the radius, and so it ends up being this. And so this last term can be thought of as the coupling constant between the temporal and the azimuthal coordinates. And this is called the Lenz-Thirring term. We can see that if the angular momentum of the black hole is really big, so the numerator here is really big, then there's a tighter coupling, okay, between the spinning of the black hole and time, right? It sort of makes sense. If it's really big, that means going really fast. We could sort of think of that speed as the thing that's coupling time stronger to the rotation of the black hole. Similarly, if the distance away from the black hole is larger, then the coupling weakens, right? That's why R is here in the denominator. Then we have C, just a constant, and G is just a constant as well. Again, G, that's our gravitational constant. C is our speed of light. And you can see like the speed of light's really big, and it's put in the denominator. So this is really a light coupling term if you think about it. But if the mass is big enough and black holes are really big, then then there's going to be some really tight coupling going on. But if you're far away from the black hole, then the coupling, again, from the inertial perspective or from the observer's perspective, is going to be really small. So we could sort of intuitively make sense of this Lenz-Thirring term. Okay. We can also define a killing vector field named after Wilhelm Killing, right? So this is not like a vector field that kills some sort of mathematical object or anything like that. It's named after someone, which is a vector field on our space-time manifold that preserves the metric. Okay. And just for illustrative purposes here, this is our killing vector field. Okay. And when we take the derivative of this, well, this is our momentum, okay? And the killing vector field, well, we're going to say that that's this right here. The killing vector field with 1 in our azimuthal component. If this is our killing vector field, what we get is this guy, okay? And then we get this guy, the 0, right? Because the derivative of this thing, of a constant, is just 0. And so the momentum of this killing field multiplied by the momentum of the black hole is going to give us a constant. We don't really need to know that much about this right now. I'm sort of just giving a little bit of background about the killing field, because we're not really going to refer to it later. The covariant time and azimuthal components of the form momentum of a test particle traveling near the black hole are computed by contracting the metric, right? So we can calculate the covariant and the contravariant parts of the momentum of some particle traveling around a black hole just by using the metric itself, right? This is how we're going to use the metric. This is really just how we use the metric that we're going to derive later, okay? But we just want to sort of take a look at this and see how the metric is used to compute momentum and stuff like that. Okay? Or, yeah, energy, momentum, and all that. So, again, we're not going to really talk about this right now. We'll talk about it in subsequent videos. I'm sort of just priming our brains here to begin to understand how we can use the metric, right? Again, the metric is something that some observer, whether it be a human or a particle, traveling near some black hole or any massive object, how they perceive time and space. That's what this metric tells us, okay? So this allows us to develop the coordinate angular velocity, I believe velocity is spelled with a C, of the particle as it travels along geodesics around the rotating black hole as well. So the angular velocity that we can calculate in this way, right? So we have that's the derivative of the azimuthal component with respect to time. When we do all this out, right, we get this g, the ratio of g theta t to gtt. That is going to be the derivative of the azimuthal component. It's just a ratio of the two metrics, okay? And that tells us something about the angular velocity. So this tells us again that the ratio of the azimuthal component with the temporal component of the metric tells us that we can calculate the angular velocity of a particle as it's in free fall near a rotating black hole, or rotating body is what I'm calling it here. This is called the dragging of inertial frames when we take this ratio between the two metrics, or the two entries in the metric, okay? So the dragging of the inertial, so we can sort of conceptualize or conceive of a particle right here, say here's our black hole's right here, and the angle by which it rotates around the black hole. We can measure the velocity, we can measure the momentum, right? We can measure the kinetic energy of the particle, and all this stuff that we can measure about the particle all comes from our metric, right? Our metric all Tells us everything we need to know about the particle around this rotating body. All right. Now that we know some of the basics of rotating bodies in space-time, we can now start to develop the Kerr metric. So, this is where the math is going to get a little heavy here. Okay, so now that we know some of the basics of rotating bodies in space-time, let's now start with developing the Kerr metric. First, we want to understand when things rotate, they bulge in the equatorial plane. So that's what we're talking about here when we're talking about oblate spheroids. An oblate spheroid is what we just talked about. We're going to have a radius. We essentially really going to have two radii here. One radii is going to be along the x-axis or along the xy plane. The other radius is going to be in the z direction, and that's r and a. Okay. So this is the radius. This thing encapsulates the two radii, I guess. And you can see how it does, right? You can see when a goes to 0, right? If there's no, when a goes to the length of r, right? When a goes to the length of r, that's going to be 2r squared, okay? And so what you get is just the square root of 2 times r times all this, right? So that, again, that's the that's the oblate spheroid. Well, I'll write that down, the oblate spheroid. Oblate spheroid. I think I spelled that right. All right. With these coordinates in mind, we can now express the Minkowski metric in oblate spheroidal coordinates. A lot of the math here is has been done on a program called MapleSoft, because there's a lot of math that goes into this, and I was skeptical about whether or not I wanted to incorporate all of the math in, and so I kind of used this computer program to just show kind of the relevant parts here, because a lot of this is going to be like tiny algebraic manipulations, easy to get lost in this stuff, but I've sort of condensed it down into a version that I think is easier to handle here. So with the coordinates in mind, we can now express the Minkowski metric in oblate spheroidal coordinates. So we have dx, dy, and dz. Dx is going to be the change in x with respect to r, like this, right? So we have all these dx, dr, right? If we just go back here, we can calculate that now. We can calculate all of these, right? So we can calculate these guys, and we get all this. Calculate all these guys, we get all this. Calculate these guys, and we get this. Okay? So nothing crazy yet, but now we can put everything into the spatial part of the Minkowski metric, right? That's dx squared plus dy squared plus dz squared. So in oblate spheroidal coordinates, this thing, right? If we were to just say that this thing is equal to ds squared, that's the Pythagorean formula, right? The ds squared is dx squared, or the ds is going to be the square root of all of this, right? The square root of this. So if we take the square root of all of this, just keeping all of this in mind, this is really just taking out the dt for a second. This is taking the square root of this thing. That's going to be, all of this is going to be the Pythagorean formula in oblate spheroidal coordinates. So what I'm doing here, we're literally taking this beast here, this beast here, and this beast here, and we are just adding it all up, right? Okay, and we're going to get these terms that, because we're squaring these things, a lot of these square roots are just going to be, are now going to go away. So we get all this, okay? And I'm not going to go through this step by step because I feel like that's just going to be like crazy ridiculous and probably not necessary. The point here is that the first step is we want to know what dx, dy, and dz are. The next step is to put that into dx squared plus dy squared plus dz squared. We can reduce all of this into this guy here, because we're now going to have, right, we have, if we just take a look here, d theta, dr squared, d phi squared, dr squared, all these terms are going to have these terms in here, right? d phi squared, dr squared, and all this. And so we can couple all that together, right? So all the things that have dr squared, this is all the things that have the d theta squared, and this is all the things that have the d phi squared. You can see this is like a friggin' beast of a Pythagorean formula. Okay? And like I mentioned, all of these expressions were used on a software package called MapleSoft, which is a very powerful package. If you download it on your computer, it's very nice. Very user-friendly, I would say. I like it. The main point with all this calculations is that we're still in flat spacetime. Okay? We're still in flat spacetime. We're expressing the Pythagorean formula. Essentially, we haven't taken the square root of all this, but this is a way to calculate the Pythagorean formula, or a line element, on flat spacetime using an oblate spheroidal coordinate system. Okay, so now let's focus on the dr term. So that's this term, right? All this right here. All right, and when we do that, we can condense all of this. You could pause the video if you want. That gets condensed all to here, and then this thing's going to get condensed to this. This thing gets condensed to this, and we get this really nice formula here. This is all of the, again, this here, this right here, is all of this right here. Okay, we can do the same thing for the d theta term. The d theta term is this guy right here. Okay. And that's equal to this, and that gets condensed down to this, gets condensed down to this, and then down to this, and then down to this. So we have this r plus a cosine squared, r plus a cosine squared. That's showing up a lot, it looks like. Okay? And then same thing for the theta term. We don't have an r plus a squared cosine squared here, but we get this right here. So now the Minkowski metric is all of this. This actually looks so much more manageable than this freaking beast right here. All this is insane, right? This is a lot easier to deal with, okay? A lot easier. So now, and we're now going to add this bit right here, right? So this here is not the Minkowski metric, right? This is the flat space. It's flat space, but it doesn't have the dt term in it. And when it doesn't have the dt term in it, we can sort of think of this as the Euclidean metric. Right, so this is our Euclidean metric. And if we didn't have the dt term, then this bit right here, right? So this bit right here is the Euclidean metric, right? Euclidean in 3D. And then the blue bit is Minkowski in 4D, because we have that term right there. All right, let's continue. So condensing things, we can write the invariant line element then in this way right here. Right, so we're going to say that this rho squared is really, if you think about this, what this rho squared is, if you just graph it really quick, we can think, rho squared, well, actually we don't really have to graph this thing, right? We could say, well, as if A equals R, not R squared, if A, I'll do it like this actually. If A equals R, we get R squared plus R squared cosine squared theta. Okay, well that is cosine squared theta plus or times 1 plus r squared, right? No. Sorry, what I don't know what I'm talking about, because r squared is what's common, right? It's r squared times 1 plus cosine squared theta. All right. And so this is what we get. And so if cosine, if theta then is, if theta is 0, okay, that's again the degree to which there's rotation, right? If we draw a black hole again, right? We have our azimuthal component is this, but then this angle is theta. So along the equator, okay, that is going to be when the theta equals 90, right? If there's no angle, if theta is 0, that's the pole. So at the pole then, this thing here is going to equal at the pole, so that's going to equal 1 plus this is 0 if theta is 0. If theta is 0, that's going to be 1, so it's going to be 1 plus 1. So that's going to be 2r squared. Okay. So this row here is really it's something akin to a radius. Okay, a changing radius. Okay. So we're keeping that in mind. So we have rho showing up here and we have rho showing up here. We have this a squared plus r squared here. All right, so this is really, again, this is just the Minkowski line element again in our oblate spheroidal coordinates. There's no cross terms in this metric, so we can add 2 that will cancel each other out. So what we're going to do now is we're going to say that this is going to be the same line element, right? So this bit here is the same here. This bit here, if we multiply it by this, and if this bit here, if we multiply it by this, and we have this 2a and this 2a, we could see that when we do that, when we multiply this with this and this with this, because this is a minus sign times a positive and a minus sign times a minus sign, well, this is going to be positive, this is going to be negative, those things are going to cancel out. But, okay, so adding these two terms doesn't do anything. But by doing this, we're able to now write this whole thing in this way, right? So this thing here is no different than this right here, okay? It's just written differently because we've added these two terms that cancel each other out, okay? It's like adding one here and subtracting one over here, okay? So now we get this bit here, this here, this here, and this here. So what did that do? All right, what did that do? That helped us. So now that we could see that as A approaches 0 and the mass ceases to rotate, then this metric is going to reduce to the Schwarzschild metric. Right, we could see that, right? So as A goes to 0, this term's going to go to 0. We get this times this. As A goes to 0 here, we get rho over this here. And so when A goes to 0, we want this to go to the Schwarzschild metric. No, I don't say we see that it rotates to the Schwarzschild metric. I say we want this to reduce to the Schwarzschild metric in the case that A goes to 0. The Schwarzschild metric has the mass of the source appearing in the dt and dr terms as well as the cross terms, so they can cancel out. This is going to suggest to us that we need to alter the first and second terms here, and the way we're going to do this is we're going to say we're going to add this little bit here, k and h, to the temporal term, or to this term here, okay, and to this term right here. Right, so we're adding and we want to know, we're adding this k and h term, and we want to know what these constants are, and we'll be able to figure that out here. All right, so what we can do now is we can say this then gets, this is the same as this if we just do a little bit more math. When we said r here, or rho again was this, rho is this, and I think that's, and then we have d theta, rho here is right here, right? So this is no different from this, but now we just have these two added terms here, and we want to say, okay, these two added terms are these things, we want them to be something, that these things are going to be something in the event that a goes to 0, right? So in a goes to 0, we want this term to come out to be the Schwarzschild metric. Okay, if h goes to 0, we want that term to resemble that entry on the Schwarzschild metric. Okay, so h and k have to be added to these terms in order for that to be the case. Okay. All right. So again, so the dt term, just to reiterate, the dt term, we want that this k and h here are going to make the r and the t terms match the Schwarzschild metric in the event that a goes to 0. So now let's do the limit as a approaches 0. So when we do that, we're going to put 0 in for a everywhere, and so what we get is this, and that we just do a bunch of math now. We get to here, we get to this, and then we get to this here, and we can see when we added this k and h, we got this right here, and we can see, okay, this is starting to really look like the Schwarzschild metric. A lot of this stuff reduced down to these guys, right? These guys, we don't have to do anything here because this is already Schwarzschild, okay? And this guy here then, and this guy, well, this isn't quite Schwarzschild yet, but we can see now what k and h have to be. We can make the following identifications, that this here has to equal this here, because this is the Schwarzschild case, and so that means that k has to equal this. This here has to equal the this case here, this here, so that tells us that h has to be this. All right. All right, substituting back into our metric, we have now a rewritten form of the oblate spherical coordinates in flat spacetime. So we put those back in, and then we come up here, and we can now make the following substitutions. We say again that this is our radius. Okay, rho here is our radius, or our combined radius, if you will. And now we identify this thing, right? This thing here is going to be a plus r squared minus this bit. And when we do that, the line element now becomes this right here. All right. Going through the math, we get here, I'm highlighting in green terms so you can follow the terms, and we get this right here. Again, like I said, there's a lot of math in the Kerr metric. The real brilliance here is this part right here, right? Where we say, okay, k and h, we want to know what these things are, and then when we took the limit as a approaches 0, these two guys came out to be what we want. K and h, again, so we're the only constants that we need to figure out what they are in order to retain Schwarzschild conditions in the event that a goes to 0. So we now make the substitutions right here. So we see, so this thing, or this thing here is this guy right here, as we see here, and that goes to this, and this here is going to be something new we identify. This is going to be this right here. Okay. And so plugging everything in now, we get this. Okay. And lo and behold, we have our Kerr metric. So when we look at this, our Kerr metric is, I'll do a different color here. This thing is going to reduce down to our short-tailed metric, but we want to now keep in mind that we have this term here, these row terms, right? These row terms here, okay. But now we also have, I'll do a different color, but we also have this term here and this term right here. All right, and then we have our A and our A here. So we have all these new terms here. When A goes to 0, rho squared, that's going to become that there's an A in rho squared also. There's an A here, there's an A here, there's an A here, and there's an A here. And then there's also A's in this guy here, and then also an A right here, right? So all of these, they're all defined, right? Like I said, they're all defined right here. But we could see now that there's this coupling term. That coupling term's right here and right here. All right. And so this is the Kerr metric, again, in something called Boyer-Lindquist coordinates. We're going to be able to understand the Kerr metric in different coordinate systems. Okay. But for right now, we have the Kerr metric, right? So the Kerr metric, we can compare this with our Schwarzschild metric as we derived in an earlier video. And we've constructed the Kerr metric. And this is different, right? It's different in that we have these off diagonal terms. We have these new defined radii. Excuse me. And A again tells us the degree of oblation that occurs in the spinning black hole. So all of this is really driven by A, right? A here, A here, A here. Everything else, you look at everything else, these are all, again, it's just R's, right? R, that's something that shows up in Schwarzschild. R, something that shows up in Schwarzschild. A shows up in this guy as well. Actually, because it's right here, I don't have to confuse things. But really, the driver here, the driver of all of these things, of all these entries in here, is A. It's all. Again, the assumption here is that the black hole is spinning, and as it's spinning, it's shrinking in the z-axis. Okay, and that shrinkage in the z-axis is what is going to dictate the components of the Kerr metric. Okay. Okay, I think that is long enough. We're at 45 minutes. Like I said, these videos are going to be a little bit longer, just so that you have more content. But with that being said, you can hit that like and subscribe button, and I will see you guys in the next video. Bye.